Let's consider our exploration of pumps with another problem involving a hot water circulating pump. A well-insulated pump is used to circulate hot water in a home heating system. Water conditions are stated. The pump requires 1/35 horsepower input. Water can be modeled as an incompressible substance with constant density of 60.5 pounds mass per cubic foot and a specific heat of 1 BTU per pound mass degree R. Neglecting kinetic and potential energy effects, determine the temperature change in degrees R as the water flows through the pump. Comment on this change. Okay, so let's lay out our storyboard so we can get a handle on this. It seems rather complicated. It's not too bad, although the units do get complicated. So let's look at a schematic of a pump, and we're just interested in the conditions across the pump itself. So there's no piping. We'll take the inlet conditions at the very entrance to the pump, and state 2 conditions will be considered at the discharge of the pump. There's no heat exchange between the surroundings and the pump, but there is power, of course. This system does not produce work, it consumes work. So the power requirement of the pump is then a negative 1/35 horsepower. And that is a minus 0.02857 horsepower. So let's look at what we know. At state 1, the pressure is 14.7 psi. At state 1, the temperature is 180 degrees Fahrenheit. The volumetric flow rate at the inlet is 0.42 gallons per minute. The density of the water at the inlet is 60.58 pounds mass per cubic foot. And the specific heat of the water at this temperature is 1 BTU per pound mass degree R. We know that at state 2, the pressure is 120 psi. We don't know the final temperature. That's what we're looking for. We're actually looking for the temperature change as the water flows through the pump. Let's figure out how we're going to model this system. Well, it's an open system at steady state conditions. We're ignoring any changes in kinetic or potential energy as being insignificant. We're dealing with a subcooled liquid that has a constant specific heat. And we want to find delta T in degrees R. Actually, it's R degrees because delta T is not a temperature. It's a number of degrees, temperature degrees. Now, we're going to assume that delta T is small. Actually, we were told that the density is constant at 60.5 pounds mass per cubic foot. But that's the same as assuming that delta T is small. And if delta T is small in a subcooled liquid, then the specific volume of V2 will be the same as the specific volume of V1. And if the specific volume is constant, then the density, of course, is constant. Let's try to put this on a TV diagram, shall we? We've got the left side of the vapor dome coming down through here. And this region out here to the left of the vapor dome is a subcooled liquid. We have a constant pressure line of 14.7 psi coming down into the subcooled liquid region. And we also have a constant pressure line of 120 psi coming down into the subcooled liquid region. Now, state 1 is on the 14.7 psi line at a temperature of 180 degrees. So it's going to be right here. And state 2 is going to be on the 120 psi pressure line. But our assumption that says that delta T is small allows us to conclude that V1 and V2 are identical. And remember that with a subcooled liquid, pressure makes very little difference. It's only the temperature that controls the specific volume. So let's write the continuity equation for this pump. We know that the mass flow rate is simply the volumetric flow rate divided by the specific volume. And since density is the inverse of specific volume, we can say that the mass flow rate, which we're going to evaluate at state 1 conditions, is just rho times the volumetric flow rate. Well, the density is 60.58 pounds mass per cubic foot. The volumetric flow rate was given as 0.42 gallons a minute, and there are 7.481 gallons in a cubic foot and 60 seconds in a minute. So I calculate a mass flow rate of 0.0567 pounds mass per second. Now let's write an energy balance. We have a process operating at steady state, so dE dt is 0, and that's equal to Q dot minus W dot plus M dot times these quantities delta H plus delta KE plus delta PE. Now, in our model, we assumed that we were going to ignore delta KE and delta PE terms, and that Q dot was also 0. So all that is left is that 0 is equal minus W dot plus M dot delta H. Well, what is delta H? We explored this in a previous pump problem. Anytime we're dealing with subcooled liquids, we can say that H1 minus H2 is the specific heat of the liquid, which is a constant, times T1 minus T2. And we're going to add to that the specific volume times P1 minus P2. So let's simplify and substitute, and we're going to get 0 is equal to minus W dot plus M dot, and then after that we had H1 minus H2. But H1 minus H2 is C times T1 minus T2 plus V times P1 minus P2. And remember again our assumption that delta T is small. If it's small, the density does not change. We'll just have rho 1 is equal to rho 2 is just equal to rho. And remember, 1 over rho is the specific volume. So let's rewrite the expression and solve it for delta T, which we'll just leave in the form T1 minus T2. So we have T1 minus T2, or delta T in this case, is W dot divided by M dot minus the expression P1 minus P2 divided by the density, and that entire numerator divided by the specific heat. So we left off at this expression for delta T, and we now know all of these variable values. We can put them into this expression and solve it, although the units get complex. We have T1 minus T2, or delta T, is equal to W dot, which is minus 0.02857 horsepower, divided by M dot, which is 0.0567 pounds mass per second. And I'm going to convert horsepower to 550 foot-pounds force per second. Now we subtract from that term P1 minus P2 over rho. So P1 is 14.7 and P2 is 120, and that's pounds force per square inch. I'm going to convert that square inches to square feet. And then I'm going to divide by the density, which is 60.58 pounds mass per cubic foot. Now I'm going to multiply the entire numerator that we've written so far. I'm going to convert 778 foot-pounds force into a single BTU. Now we have to divide it by the specific heat, which is 1 BTU per pound mass degree R. And when we plug all this into our calculator, we get T1 minus T2 as minus 0.0345 degrees R. Now, if it were T2 minus T1, we'd have a positive number. It doesn't really matter which order it's in. We see that T2 is ever so slightly greater than T1, but it is a tiny number. It's 0.03 Rankine degrees, which is the same as a Fahrenheit degree. And of course, a Rankine or a Fahrenheit degree is about half the size of a centigrade degree. So this is truly a very small temperature change. And so we can draw two conclusions from this output. The assumption that delta T is small is validated, and so that validates our model. And it also is why we typically assume that liquids maintain a constant temperature when flowing through a pump. The amount of energy they pick up in the terms of a temperature increase is very, very small. And so we generally assume that the temperature rise is 0.